All right. Good morning, everyone, or afternoon if you're on the East Coast, and welcome to the National Electric Code class. Just a word of caution: this is the very first time for us to teach this class, and it's going to be a slog. It's going to be a start to finish kind of review of National Electric Code, and we're going to focus on solar power and building electrical systems, generators, batteries, with the idea that we need to be familiar with how all of our on site distributed power resources interact at the electric service panel and at the point of interconnection. If you're like me, you got into the solar industry because you wanted to do solar, or you might be an architect or engineer where normally you would put install per national electric code, onto your building specs, and a general contractor would take it from there. But maybe now that we're getting newer technologies, LED lighting systems, lithium ion battery banks, solar power, you know, building design in the electrical system requires more expertise. But at that point, you might train up on just one section of National Electric Code and never get around to reading the others, other than just what specifically pertains to your system. And what that means is the main parts of electric code that govern the entire part of your solar design or what have you. It's just normal electrical requirements that a general contractor might know. Common wiring practices, cable selection, raceway selection, breaker sizing, just standard electrical practice. But the expert on the project, the solar guy, the renewables guy, uh, they might know everything about section 690, the photovoltaic section, but then the rest of their knowledge is, might need a little bit of improvement. And so we're going to review electric code. Most of our course content is going to draw from the first four sections of class, which govern all electric installations, and then tomorrow we'll be spending more time on the specialty equipment, solar and battery banks, unless this gets too dry, and then we will just go into a take a break and do a design exercise or something like that. So it does qualify for NABCEP recertification hours. I myself am a NABCEP solar installer, so this will have a solar power, I guess, flavor to it, if not the focus. But again, architects and engineers can benefit by just learning more about the NEC to better talk with their on-site contractors. In other courses we say, well, there's a big opportunity here for architects and engineers to work with general contractors, but you got to be able to communicate. And even if you go into the NABCEP community and bring a NABCEP PV expert on board, there's a lot of quality improvements and cost savings we can have by, you know, optimizing that collaboration between the designer, the solar specialist, and the general contractor. So with that, let's just go ahead and dive in. And I apologize, I'm losing my voice a little bit. So this is going to be a painful class in more ways than one. But one difficulty in teaching National Electric Code is that we're not allowed to just replicate the code in a handout or presentation. Code is really by reference only, and the reason for that is the National Fire Protectant Agency. Now, the guys who set the standards for the codes, they make money off selling the code books, and that revenue goes to maintain the quality and administration of the National Electric Code. What's surprising about code is it's not a public resource. It's produced by a private organization, and it should be referred in documents and specifications by reference only. You're not allowed just to reprint the code verbatim. So it is protected by copyright, and you have to buy a copy of code to read through it. If you're going to be an electrical designer, you can't just find online access to the entire code book for free. Now, I have to say the National Electric Code books that I've bought have all been paperback, but also of exceptional quality. I just recently bought a copy of National Electric Code 2017, which I think is a great improvement from 2014. I really like the changes they have made. And I previously had NEC 2011 book, and I was able to sell my NEC 2011 because even though I am not I don't have many, I can't really take care of nice things, and it's a 7-year-old reference manual that I use on a frequent basis, both on and off the job site. It still had held together enough to be able to sell online. So there's even though you really have to buy an actual copy of the code to really delve into it, it's well worth the money to just go ahead and do that. Now, for that matter, National Electric Code is not designed as a specification or instruction manual. So it's not there to enable a do-it-yourselfer to install their own solar array in lieu of hiring an electrician. And the spirit of this course is to enable you, if you're unfamiliar with electrical components and National Electric Code, to be able to talk with your electrician on the job site and make sure that if he's new to solar, he doesn't miss anything, or if you're new to balance of system material design, that everything gets picked up. But this class as well is not intended to render professional advice specifically. So, we have to disclaim liability for use of the code and the content in this program before we move forward. So just consider this information so disclaimed. And then let's get to the beginning. So the first section of National Electric Code is definitions. And we're going to leave the definitions for later when we, as we get to the words in the code, then we'll bring the definitions up on screen. But before we get started, just some additional notes. Code is intended to be a minimum set of safety requirements, not a maximum set. You will encounter situations where you might be in the attic and you might say, okay, well, this attic is a dry location, but because I'm poking so many holes in the roof, should I consider it a damp location or a wet location? Well, code only says dry location. That doesn't mean you can't, apply common sense and make your design more robust. Then again, you can't just go willy-nilly substituting products. There might be a difference between a bundled dry cable and a single conductor wet cable in the eyes of code, and we need to figure out what those nuances are in order to kind of perfect our solar design. And code applies to both public and private premises, as well as mobile premises like RVs, parking lots, yards, temporary businesses like I guess like a sound stage or something like that. All of these things are governed by electric code as well as the point of interconnection. Okay, so we start out with the basics. We define all of our terms, and then we get into installation requirements. And what we'll see is code takes that philosophy and and runs with it for the next few sections. So the beginning sections of code are kind of establishing the ground rules uh, for for terms, for supplying power to the building, for what supplies power to us. But before we get to the building, we have to talk about what supplies power to a panel. So we're defining our feeder circuits in our then getting into our wiring methods, and then later on in code we get more complicated. Now that we have feeder circuits defined and wiring methods defined, then we get into the sizing of conductors and cables, then we get into general equipment, and only later in code do we get to the specialty stuff like solar arrays and distributed power. So there is going to be some repeating content in code as we move along, because what is relevant to, say, the utility feeder conductor might also be relevant to an AC branch circuit that is later defined in code. So there is a lot of repetition, and what that means is if we start at the beginning and really understand the reasoning behind all of these terms and conditions, then we will be better able to comprehend and understand code in the later sections. And also, you can prepare for your master electrician exam. And when you get questions about motors or other things that you're swimming pools, you might think to yourself, well, I don't know about swimming pool design specifically, but now I know about running conduit through concrete. So what about that knowledge is relevant to swimming pools? Things like that. Deteriorate agents. No conductors or equipment shall be located in damp or wet conditions, exposed to gases that have a deteriorating effect or excessive temperatures, unless identified for that purpose. So, solar arrays and generators are usually outdoors, and that means they're exposed to the elements. If they're protected, if they're sheltered outdoors, if they're not subject to water spray on a regular basis like rainfall, that's not necessarily a wet location. That could be a damp location. You can have interior wet locations. A wet location is something that gets sprayed with water. So a car wash might be inside of, might be enclosed, but that would be an interior wet condition. Um, Usually, a rooftop would also be a wet condition. Now, solar arrays and rooftops undergo extreme temperatures in addition to a wet location. And then in some solar arrays are exposed to gases, so flooded lead acid batteries, and generally any kind of batteries that require watering and regular maintenance will emit gas that has a deteriorating effect on metal. And so in solar power, we have a lot of specialty cabling and equipment, and it's not so much that the cable is particularly unique. It's not like a fiber optic cable that has a billion different connectors to it. It's a single conductor cable, and you might go into Home Depot and think, well, there's a billion single conductor cables out here. Yes, but are all of them listed for wet conditions? Are all of them listed for excessive temperatures? And so what's complicated about on-site renewable design is that if you're a general contractor, general electrician, you just may not connect all the dots through on saying, well, what's the difference between a wet location and a dry location? You might get to the store and realize, well, this cable is not listed for outdoor use. So we have to learn how to match all that stuff up. So a damp location would be under a porch, a basement, some warehouses, car washes. A wet location, a concrete slab is considered a wet location. So I think that's kind of one of the more, I guess that's you'll experience that a lot. Areas exposed to water saturation, unprotected areas exposed to weather, dry locations. That's like the inside of your house. It can be temporarily damp or wet during construction. That doesn't mean it's a dry location. Now, I can tell you from industry experience, the locations can trip you up and weather ratings can trip you up because solar equipment is so robust and it is designed for outdoor use. So you might be buying inverters that are NEMA 3R or even sometimes NEMA 4 or even NEMA 6. So very robust, waterproof inverters. You may be buying micro inverters or module level electronics that go up on the rooftop, and they have, they're listed for the extremes and they're listed for the weather. Same with solar modules. Your solar panels are designed to go up on the rooftop for a long period of time as well. The danger is during construction, if the array is not complete, fully complete, you might have loose connectors and wirings hanging off all of these components. And I have seen damaged electronics where the install crew might mount the optimizers or microinverters at the end of the day, and then they don't plug them up and it rains overnight. Water gets into the connector. Or inverters stored out on a job site with a tarp over them, and they're a NEMA 4 inverter, but then something goes wrong with the construction of the ground mount array. The material sits outside. It rains a while. Humidity gets under the tarp and into the box and starts deteriorating the electronics because they're not fully plugged up yet. So don't confuse if you're designing something for a wet environment, when it's not installed, that doesn't mean it's still rated for the wet environment. Um, and, that can be a very costly mistake. So, think about your locations. It makes, you might worry about temperature sizing. Do I use a 75C cable or a 90C cable? Well, if you're up on the rooftop, that's a very hot environment. That's what the high temperature cable, the 90C cable, is designed for. So yeah, you should use a higher elevated temperature cable on a rooftop. Inside your conduit, inside the attic, where you see this conduit going up to the rooftop. Well, that conduit is not just in the attic; it's going up to the rooftop, and we'll see code requirements that say at that point you need to put foam sealant into that conduit, because what can happen is the temperature difference between the attic and the atmosphere can cause condensation and moisture, and water can get into that conduit. Or likewise, the conduit that's buried into the ground, that's a wet location. Inside the conduit, it's going to leak. It's going to get humidity into it, and that's considered a wet location too. So you don't need to worry so much about your material selection and what wire type you're using if you start with the premise of, okay, is my environment wet, damp, or dry? Is it going to experience high temperatures, or is it air conditioned and inside? Are there any batteries in the room, so I have to worry about a corrosive environment? Or am I right on the coastline, or am I on a chicken farm? What's a corrosive environment versus if there's no gas in the area? And from that point, that's what drives your material selection. Okay, other installation requirements, connections. So the temperature rating associated with the ampacity of a conductor shall not exceed the temperature rating of any other connector termination, conductor, or device. And what that means is often you'll have a off-the-shelf part, like an off-the-shelf disconnect that you might get from Lowe's or Home Depot. And that disconnect is may not be designed for being installed on a rooftop, and so it might have a lower temperature connection that is sufficient for, you know, for most of for most of its uses. But then again, you may have a conductor that goes all the way up to the rooftop that has a higher temperature rating than the temperature rating of the disconnect. So it's common to have a disconnect switch with a 75C, a 75 centigrade terminal. And now in a renewable energy system that's exposed to the direct sunlight, your cables have a higher temperature rating of 90C. And so what do you do your calculations at? Do you do them at 90C because you're using 90C cable? And you can use conductors with temperatures with higher ratings for ampacity adjustment and correction of the cable. But you also have to make sure that even though you're doing this ampacity adjustment and correction, that the temperature at the terminal is still not exceeding 75C, or its rated temperature. But that's usually what that means is on your balance of system material, on your conduit, on your spec sheets, you're going to see the temperature labels listed and rated for that. And you can find in the solar specialty equipment boxes that have 90C terminals, and they usually cost a little bit more, but that might gain you a smaller wire gauge that because of not needing to do the temperature derating calculations for the 75-degree terminal. And that's going to come later. That's going to come in section 300. So we'll probably get to that after the break a little bit later today. Uh, you might be asking yourself at this point, well, where do I go and get design temperatures? How hot does it get up on a rooftop? How hot are my modules and my equipment up there going to get? And actually, we can, for your design work, you're supposed to use the ASHRAE database, but that ASHRAE database won't convert from the ambient temperature to that rooftop surface. If you want to get an idea of what the module temperature is, we can go back into PV Watts, which we've explored in previous classes. So in PV Watts, you go and get that monthly weather data, and we see from our PV Watts output for every hour of the day, for every month of the year, we get not only the output, the power level of the system, but we will get what the ambient temperature was for that simulated day, and then also what the cell temperature was for that simulated day, so that we can see on this 12-degree centigrade day at noon, the module surface temperature got all the way up to 24C. So I'm not particularly good on my centigrade to Fahrenheit conversions. But let's just go 12C to Fahrenheit. So on a 53-degree day outside, the module surface got up to 75 degrees. So that's actually kind of even though it could be jacket weather, cold weather outside, the module surface could be elevated by 20 degrees. So on a hot day, when it's 100 outside, how hot does the module get? Well, let's find out. Here's an example for Phoenix, Arizona. On a 99-degree day outside, it gets all the way up to 160 degrees Fahrenheit on the rooftop, or 71C. And commonly, the wiring that's rated for inside your home only has that 75C rating, or maybe even less. And so, it's very possible for wires on a solar array or on your rooftop to get to a temperature beyond 75 C. So if they don't have that 90 C rating, they could start burning up on the rooftop. So just because you have a 60 or 75 C cable and it might have all the ampacity allowed for your application, if it's going to be subject to direct exposure to sunlight, you can't just oversize the cable to reduce its temperature. You need a cable jacket that is rated for that elevated temperature. And we apply discount factors to make sure that the cable does not heat up enough. And when you get into higher and higher temperatures, two things happen. One, you're operating at elevated temperatures, but two, you're buying a more robust cable jacket that can contain the heat of the conductor and not start burning up on the rooftop. And so, when you go and you use cables with more robust jackets, you can get away with less derating of your conductor. Derating the conductor means you're increasing the conductor size. When you increase the conductor size, the resistance of the conductor goes down. It's more efficient and it generates less heat. And so in solar design, and when you're transmitting electricity from a generator to its point of use, you're balancing the environmental conditions, you're balancing derating the conductors, but then there's also efficiency, where often you're upsizing the cables anyway in order to make the system a bit more efficient. So we'll run through these calculations as we get into those sections a little bit later on in the program. But right now we're still back in section 110, installation requirements, spaces about electrical equipment. Electrical equipment needs space. In addition to being firmly secured to a building, not just resting on the conduit that comes up from an underground conduit run, but actually securing the box or metal to the building itself. We need to maintain space around our equipment, and that zone extends in front of the panel and above the panel and under the panel into the side of panels. And so just by looking at this room, this is a messy room, and there's also requirements to install your electrical equipment in a neat manner. And so we can see, say, this fiber optic networking equipment to the left of the service panels. That's not a code violation in the sense that it occupies the same working space of the panel. They're both electrical equipment. Where the code violation would be is that's not installed in a neat manner. And then there's other code violations too. That duct work above the service panel needs to be of a certain height. All of that can be found within National Electric Code, and including spacing from your plumbing. And you see here that hot water heater is likely too close to that fiber optic equipment. Actually, though, fiber optic equipment is dealt in its own section of code, section 800, down at the far end. It has more leniency than other sections because fiber optics is a extremely low voltage system. So, fiber optic systems often will operate around 2 volts, whereas, with tiny little cables. Solar arrays, wind turbines operate at battery chargers, lithium-ion battery banks operate at 3, 4, 500 volts, even all the way up to 590 volts under normal operating conditions. They're high voltage, they're dangerous. Generally, if you're a commercial electrician, you have a more rigorous oversight by the state and you're dealing with higher voltage systems, 480 volts instead of 240 volts. Solar arrays can go even higher than that, but not always are they being installed by electricians on the job site. And so the depth of the working space, how far back does the equipment need to go? That has special rules for what is behind the panel as well as what is in front of the panel. The maximum space is around 4 feet, and the minimum space is around 3 feet. And so if you just keep in the back of your head, well, in the depth from the face of the panel, you need to have around 3.5 feet of working space. And if the room is feeling particularly tight to you, rather than the panels being back to back, or depending on what is on the back of that panel, you may need an additional 1/2 foot. The width of the working space, 30 inches, or the width of the equipment minimum. And that can actually be on either side of the equipment. So you at least need to have the width of the equipment clear at minimum. And then you need, beyond the width of the equipment, a minimum of, from one side to the right or the far side to the left, 30 inches of working space. Now, whether or not that working space is centered or offset doesn't really matter so much. And then the height of the working space. So it's 6.5 feet, or the height of the equipment. So obviously, if the equipment is 8 foot tall, it needs 8 foot clearance. But if it's only 3 foot tall, like this electric service panel, the working space is 6.5 feet. And so the question is, well, is that air conditioning duct a code violation or not? You walk through the door, you see the service panel, you see other code violations, and you might look at that air conditioning duct and say, I wonder if that's a code violation too. And for that electric service panel, it might be that air conditioning duct is in fact 6.5 feet tall. And so from the floor up to 6.5 feet is 6.5 feet of clearance. And where these requirements get tricky is especially when you're involving battery banks. Because if you're doing, say, an off-grid residential home, you're likely working with lithium-ion battery banks, and these things are huge. I have such a home of one of my project sites, and this is how the architect sketched up the room inside the garage. That's going to be an air-conditioned space where we're putting our inverter equipment and our battery bank. And while there's a sink and a fridge and a desk in here, the client said, we're not really, we can remove the doors and the windows. This is going to be for the inverter room. You can use whatever space you need, but we would like to locate it on the walls. Well, here's our batteries. Now, our batteries are, let me see if I can't pull my laser pointer up here. Our batteries is right here. So our batteries are 38 inches deep, 9 inches wide, and 2 feet tall, and they weigh 1,000 pounds each. So these are hefty, large batteries, and we have 8 of them on the job site. Here's a picture of 10 batteries. I think these are gel batteries rather than flooded lead acid. But what we can just see is off-grid homes, the battery banks, if you're using flooded lead acid type, which generally you are because it's the cheapest and has a lot of market ability, and as of now it's still kind of hard to purchase lithium-ion batteries in the US. So the question is, do you have space in your room for these batteries? And also just the practical element of how are you going to get the batteries to the room if you're using heavyweight batteries. Those are issues we talk about more in the battery management class, on why you might choose a 2-volt battery to have 48 batteries in your battery bank instead of a 12-volt battery and have 8 batteries in your battery bank. It's all about, can you move the batteries around, or do you have to carry them in? If you have to carry them in, you might go with the smaller, more lightweight battery and have dozens of them. Well, back on point, this is our inverter system, and we have 2 inverters, and we have electric service panel, and then the 4 objects on the right are the charge controllers. And so in total, our kind of inverter control system wall is 8 feet wide and only 9 inches deep. And so in our case, the 6.5 feet clearance is no problem. There's nothing else going to be along the walls of the building. But going back to our room, if we need 8 feet for our inverter system and our batteries, if we have 8 of them and they're about a foot wide each, you know what? In total, our battery bank plus our equipment is 15 feet wide. And then we need 30 inches on a side of each. And so we and then we need 30 inches in addition to that. So what we really need for a code compliant room for the minimum space requirements of this electrical equipment is really a 16 or 17, actually an 18-foot wide room. And we don't have that. Well, I guess we could use that along the back wall. And so this essentially says, well, where are we going to locate our inverters and our batteries if we just want to use a single wall? Can we put them here, or can we put them here? Well, we don't have enough space along this wall to put them here. We'll have to use this wall instead and, get rid of that desk and put the batteries along this wall, because that's the only wall that has enough space. Alternately, we could catty corner them and get rid of this doorway and put them on a corner here and a corner there. And they say, well, can you stack them on top of each other? Is it possible to, let me get my pointer back. Can we instead kind of, instead of catty cornering them, can we stack them on top of each other? Well, then that we have to consider all 3 dimensions, height, width, and depth. And there's another part of code right after this that says above or below any electrical equipment, other equipment shall not extend more than 6 inches out. And so you can't have one piece of equipment that sticks far out from the wall and another piece of equipment that's kind of inset into the wall stacked on top of each other. Those technically would be different zones. It would violate, you would need 2 different working spaces. So to put them on top of each other, you'd have to have a 6.5-foot section and then another 6.5-foot section, although that would be very impractical for the most part. And so what we have is, the reason why this would be a violation, going back to our spec sheet, is this equipment only sticks out 9 inches from the wall, and these batteries stick out 38 inches from the wall. And so if a client says, I want to use this wall, and you might think, okay, on these charge controllers, they're just kind of, there's not much going on in those charge controllers. There's 4 of them. There's no disconnects. It's just 2 wire terminals each. There's not much going to fail with the charge controllers. The client's never going to need to access those charge controllers. And so I'm just going to put them above the batteries rather than to the side. That would be a code violation as well. And so we look in these rooms, and the question is which of these rooms is compliant or not. These both would be considered damp locations. There's actually a few points about this array that are not compliant. The first is the depth. You know, the batteries stick out more than 6 inches from the service panel. Now, we do have 6.5 feet of just electrical space, and we do have the width of the equipment or 30 inches of access on this side, aside from that depth violation. But then we also have some other items of concern. You know, the first is the deteriorating agents of these batteries could expose this metal conduit. And you can see this installer didn't care because they're capping their batteries and ventilating the gas out of the building. But you can imagine a local inspector might say, well, that's not good enough. You know, what I want this to be is in, electrician's gray conduit. Well, then the solar guy might say, oh, but it's a DC circuit. And DC circuits have to be enclosed in metal. And that's why we did an EMT conduit. And the inspector might come back and say, well, you know, that may be the case, but metal conduit still can't be in a battery room. So, you know, what you need is a metal conduit with a PVC coating around it, like that flexible metal conduit. Depending on how tough your inspection is, you know, what we can see is here. It looks like they're going into a PVC bend at this point. So that is a code violation from clearance, and your batteries also need to be accessible for servicing. And so if this end of the battery bank uh, needs to be serviced, and they have a watering system, and so they may only need to access this end of the battery bank, but accessibility of both ends of the battery bank may also be a concern. All right, so let's get into some definitions. Ampacity is the maximum current that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Voltage is the greatest potential between two conductors of the circuit. And so we think about that boulder sitting on the very top of the mountain at a high potential energy, and if it crashed all the way down the mountaintop, if a group of mischievous Boy Scouts pushed the boulder off the mountain and it careened down through the forest, it'd do a lot of damage before coming to a stop at the bottom of the mountain at no potential energy. Well, voltage is not potential energy. It's not the stored energy of the boulder versus the boulder at rest at the bottom of the mountain. The conversion of kinetic energy or moment, potential energy into kinetic energy. The voltage is not potential energy, but it is a potential. It's a difference in voltage that makes the difference. It's the voltage of your high voltage line versus a zero voltage line that causes those electrons to be pushed from high voltage into low voltage, just like that boulder would be rolling from energy from its high potential energy to its low potential energy. Electrons flow from a high voltage potential to a low voltage potential. And so then we have voltage to ground. And it says for grounded circuits, the voltage between the conductors and the grounded circuit conductor. For ungrounded circuits, the greatest voltage between the given conductor and any other conductor of the circuit. Okay, well, there's a lot of word salad in that. What does that mean? Well, what that says is you have a grounded circuit conductor, which we haven't defined yet, and then you have ungrounded circuits as well, and they're going to have a difference in voltage potential, and the greatest difference in voltage potential would be considered the maximum voltage to ground. And then you also have nominal voltage, and nominal voltage is the kind of at some point, what voltage level we operate our equipment at and design our equipment for is a function of how we convert electricity from a low voltage to a higher voltage, and down to the brass tacks of how many times do we wind a piece of copper around our electric generator in order to step up that voltage. And so, just kind of by tradition, we manufacture transformers at 120, 240, or 480, 277, or 600 voltage, 600 volts. And the actual voltage inside that circuit can vary based on what type of transformer it is under normal operating conditions. A great case in point would be a battery bank that is rated for 48 volts. And you have a 48-volt battery bank, but you might, for certain batteries like flooded lead acid batteries, have a maintenance feature where you drive the battery bank voltage up beyond 48 volts into the 50 or 55 volt range. The battery may be designed to take 60 volts, but its normal operating voltage is 48 volts, and that would be the nominal voltage. But generally, you don't design around the nominal voltage. Generally, you are designing around the maximum circuit voltage. And then, you also have to consider your operating conditions as well. And that might mean that, sure, a solar array is going to be operating at 30 volts on its spec sheet, and that would be considered the nominal voltage. But its maximum voltage may be something different. Its maximum voltage may be a function of temperature. And so we have to apply temperature correction of factors before we get into our design to make sure those conductors don't burn up. Some other terms: branch circuits. Branch circuits are those AC electric circuits in your home. Solar circuits are not referred to as branch circuits. They're DC instead of AC. And so your solar circuits, instead of being referred to as branch circuits, they're often referred to as strings. It's just industry jargon. But they're also referred to as code as something completely different. So you could have an AC branch circuit on a microinverter array that would be a solar inverter output circuit. Or you would have a DC string running between your array into the inverter on the side of the building, and that would still be, it'd be a DC string. It would also be a different circuit category, the photovoltaic array output circuit. Get into that tomorrow. Continuous loads: a load where the maximum current is expected to continue for 3 hours or more. So what does that mean? Well, we have electrical appliances in our home that work all day, and then we have electrical appliances that we only use for 20 minutes at most a day, like your microwave. And so that gets into a difference between continuous and non-continuous loads. So the question is, well, what would a solar array be? What would a wind turbine be? Would it be, do we size it as a continuous load or a non-continuous load? What about a backup generator that's only going to hang out on the back of your house and not do anything unless you lose power? And a power outage may only last an hour. So is that a continuous load or a non-continuous load? Generally, you have to think about the intended use of the device. That backup generator, even though you might only be using it an hour every 5 years, it's intended for full-time use. A solar array turns on in the middle of the day and it turns off at night, but in the middle of the day it's operating for more than 3 hours. And so a solar array is considered a continuous load rather than a non-continuous load. And so on continuous loads that are under regular continued use, you will apply safety factors because those cables are under continuous current. You know, they're always on, they always have some heat in them. Their starting point is an elevated temperature, as opposed to the non-continuous load that is usually off but occasionally turns on for no more than 3 hours. And so for non-continuous loads, you may not have the extra ampacity requirement that continuous loads have. So like with the solar array, you apply a extra 25% because it's a continuous load. And then you might also find yourself applying additional corrective factors. But if you think about it as, okay, is this a continuous load? Yes. Okay, I've applied my 25%. Well, have I adjusted for temperature? No. Okay, well, I still have to do that. You know, you start being able to understand all of the factors that need to go into your calculation. So which of these loads are continuous? You know, we have the refrigerator, the solar array, the washing machine, and the air conditioner unit. Now, your refrigerator might have a duty cycle where it clicks on and then it clicks off, and then it clicks on and then it clicks off. And the same thing with your air conditioner. You know, we already talked about the solar array. Now, really, the only non-continuous load in this list is the dishwasher, because it's not operating 24/7. I mean, that even though the refrigerator is going through a duty cycle, it's 24/7 operable. It doesn't just operate for 3 hours or less. Same thing with the air conditioner. Article 210.19, conductors, minimum ampacity and size. So we have branch circuits that are sized for not more than 600 volts. And then sometimes in code, there's other sections for circuits that are greater than 600 volts, which get into non-residential electric services. We can see a reference later in the code for sizing. We can see references later in the code for motor circuits. And then we see a voltage drop requirement that says voltage drop should not exceed 3% at the furthest load or 5% to the furthest outlet. Well, in the solar industry, we're usually designing for a 2% voltage drop or less. So we're upsizing our cables for voltage drop, and we would not violate this code. And, you know, it's usually cost effective to spend a little bit more money on cable and make it up in efficiency gain. So yeah, not trying to get the 5%, but going for a 2% is kind of the more sane, rational approach. And since we're on the topic of voltage drop, what does a 5% to the furthest outlet? Now, what would that mean for AC or DC circuits? I put DC in there, but actually AC is less efficient than DC. You know, DC goes from that high potential all the way down the mountain to its low potential. AC wiggles back and forth. And that wiggling produces a little bit more heat, a little bit more resistance. And so actually you'll get, if it's the same voltage level, the same cable, the same conductor on AC versus DC, the AC system will just produce ever so slightly less power. So what does this mean? What does a 5% voltage drop really mean? Well, what I'm thinking about is tiny homes or RVs. People say, well, I want to convert my clubhouse or my tree house or my hunting cabin or hunting shack into a solar array, and I want to run it off a 12-volt battery. Well, if we're using number 8 copper at 12 volts, I'm going to exceed a 5% voltage drop anything outside of a 20-foot perimeter of that battery bank. if I'm using number 8 copper, which is pretty, that usually is about the maximum size you go up to before the components may not, lower power components may not accept larger cable than that. And so, it might work for a recreational vehicle that's no more than 40 foot long to have a 24-volt battery bank. But then if you want to do a off-grid house, and it's not a tiny house, but it's an actual house, it's not a yurt, but it's a home that most people would be familiar with, want to be comfortable living with, you wouldn't want to have that be a 48-volt battery bank where you're just running it off of DC only circuits. And it doesn't have anything to do with the DC, whether it's DC or AC, really, although finding equipment might be hard if you're running at oddball DC circuits. It's really more to do with the low voltage of a 48-volt battery bank. We want to step that voltage up so that we can push it further. So your 120-volt circuits and your AC service panel can push electricity a lot further than a lower voltage DC circuit. All right, let's define a term. Feeder. All circuit conductors between the service equipment, the source of a separately derived system, or other power supply source and final branch circuit over current device. So what we're talking about is anything between the generator and the breaker switch on the panel that the generator provides. That's a feeder circuit. Similarly, your grid connection is the same. It's from the grid to your main service panel. That's a feeder circuit. So from power sources to the feeder, the main service panel, the load panel that they supply, that's considered to be a feeder circuit. And so where's the feeder circuit on this graph? Well, here's our in-phase microinverter AC branch circuit. And then it's landing on our load panel. We actually have two feeder circuits on this. We have the feeder circuit from the utility coming in, and then we have the feeder circuit from the solar array coming in to the bottom of the bus bar. And so now we're getting into section 200, and we've defined all of our terms, and we've talked about clearance requirements and general installation rules and regs. And now we're getting into how do we supply power to our load. And it says we have different rules for feeder panels of 600 volts and lower versus larger commercial systems. When you get into those above 600 volt systems, you may have less requirement in some areas because you also have more requirements in others. So there may be a requirement for an engineering calculation. There may be a requirement for rigid metal conduit. There may be a requirement for, I don't know, additional protective relays. And so that might be, you also gain some cost efficiencies of using higher voltage equipment. And so that's great too. So when you get into higher voltage equipment, there are perhaps some cost savings on the overall system, even though individual components you're spending more money on that, and you'd have to buy different things for higher voltage commercial systems. But anyway, feeders that are under 600 volts are sized on 125% of the continuous load plus the non-continuous load. So the continuous load, because it's under full-time operation, gets adjusted a bit more than what a non-continuous load would do. Overcurrent protection. Feeders are protected against overcurrent by an overcurrent protection device. And so what is an overcurrent protection device? It can be a couple of things. What we're familiar with are breakers on our electric service panel. Those 20 amp breakers go over 20 amps. That's an overcurrent protection device. But A fuse is also an overcurrent protection device. And so a fuse, as opposed to a breaker, will burn up and not work rather than just trip. You might say, well, why would I want a one-time use fuse rather than a breaker? And the answer is, well, cost. It's not going to happen. If it does happen, you want to know why it happened anyway before you really operate it again. A fuse may be perfect for the job, although breakers may be more simple. It also might cost more. Regardless of whether you use a fuse or a breaker, you're using an overcurrent protection device. And so if you have one circuit and there's a fuse on one end and there's a breaker on another, that circuit has two overcurrent protection devices, and it's a little bit redundant, and not necessary in most cases. Let's keep going. Get into some more definitions. Ground is the earth. Grounded is connected to ground or to a conductive body that extends to ground. And the equipment ground conductor is the conductive path installed to connect non-current carrying metal parts to the system grounded conductor or to the grounding electrode conductor, or both. So very quickly into the section 200 and 300, we're going to have these terms coming at us: the neutral wire, the grounded conductor, a ground plate, a ground rod. And we it's important to understand what these are. And for now, just the equipment grounding conductor, the EGC. So the equipment ground conductor is the path that is put in place to connect metal parts of your system to ground. So if you have a metal box, if you have a metal fitting, if you have a metal bar inside your plastic box, your metal module frames, your metal racking systems, all metal parts have to be connected to ground. And the system in the building that connects those metal parts to ground is called the equipment ground conductor. And so what's ground in this picture versus the equipment ground conductor? Well, we got here's our ground. This is our connection to ground. And our equipment ground conductor is this green wire that is connecting to our microinverter box and connecting to our modules. And this can be a few things. This could be copper wire that is landing on a ground lug between module to module to module. The racking system itself may be listed as a ground path. And so you might have a grounding washer that connects the module frame and the microinverter to the racking system. And the racking system may land on a box that has a bare copper or green wire going up to the rooftop. So this green system, how the all metal parts are connected together is part of your equipment grounding conductor system. And then the ground is down here at the bottom. So where in my slide go? There we go. So then we have the grounding electrode conductor. And then another term, the service conductors and the service point. And so what is the grounding electrode and the grounding electrode conductor? The grounding electrode is the object that establishes the direct connection to ground. So whatever this, you may be familiar with this little triangular symbol as ground, but whatever that physically is on the job site is the grounding electrode. And we have a special term for this cable that connects the ground to actual ground. This kind of end of the line cable that goes directly to the physical object that connects to ground is the grounding electrode conductor. And so the question is, well, how is the equipment ground conductor separate from the grounding electrode conductor? One's an EGC and the other's a GEC, and they have the same words. So what are both? And the answer is, well, they're both very similar, but this one wire is kind of the end of the line. And so whereas the equipment ground conductor may be sized for each individual component along this circuit, the grounding electroconductor is sized for everything. So it's going to be sized off the service itself and be a little bit thicker and have some unique safety requirements to it. And so, you may need a system ground, an equipment ground conductor, a grounding electrode conductor, and you may have we really haven't gotten yet to the grounded system conductor, service conductors. What's the service conductor and the service point? Service conductors are the conductors from the service point to the service disconnecting means, and the service point is the connection between the facility serving utility and the premise wiring. And so here we have our electric meter, and then we have our premise wiring, and often that meter is considered the disconnect and the service point. And so the service conductors are coming from the service point to the service disconnecting means. So they may be talking about from the transformer up to that meter itself, and then the point of the connection between the facilities of the utility and the premise wiring being the service point. And usually it's governed at that meter. We get another definition. We're going to say feeders shall not be derived from auto transformers unless the system supplied has a grounded conductor that is electrically connected to the auto transformer grounded conductor. All right, so what the heck does that mean, and how does it apply to solar? I've never seen an auto transformer in a solar array until I started to get into battery banks. And so here, SMA has a very popular auto transformer, and it needs one because if my voice gets too squeaky, just send me a message and I'll take a sip of water. But it needs one because the SMA battery inverter is designed for 120 volts. And if it's going to be grid connected, that voltage needs to step up to 240 volts. And so it's a grid connected inverter that has a 120 volt output, and we need to step that voltage up to 240 volts for it to be compatible. And so here is our battery inverter. And here's our transformer and distribution box, where we are taking the output of the Sunny Island and turning it into a 240 volt leg 1, leg 2 neutral output. And so going back to the code, we have a feeder circuit from the battery bank supplying power to our load through this auto transformer. So what do we have to do? The system grounded conductor needs to be electrically connected to the auto transformer grounded conductor. We still don't know what this grounded conductor is. We haven't defined it yet. A grounded conductor is a system or a circuit that is intentionally grounded. So a grounded conductor is like this green conductor that is intentionally connected to ground. So is this the only grounded conductor in the system? What we're talking about in this case, when they refer to a grounded conductor, is this neutral wire. So we see this neutral wire that is connecting to the sunny island, to the neutral of the sunny boy, to the neutral coming in from the electric grid, maybe even from the neutral of this generator. They're all sharing a common neutral. And the reason for that is that the neutral will help all of the breakers and overcurrent protection devices in the system work. The neutral is not a zero voltage system. The neutral is a helps complete the circuit for these systems, and if there's ever a ground fault, the current in the neutral helps lift the breaker at the breaker switch. And so here we have our sunny island, and it says, feeders shall not be derived unless the grounded conductor is electrically connected to the auto transformer. You may need to share, tie in the neutrals together of all these systems. And then there's going to be a rule on how that neutral is connected to ground later. So the neutral is a grounded conductor, but where it connects to ground is governed by very specific rules. And so the point is, you may have a generator providing its own neutral. You may have the utility providing their own neutral. You may have a transfer switch and a solar array. And if these are all going to be operating on a shared, on a non-separately derived circuit, their neutral system has to be interconnected. So then we have voltage mandates that says unless there's special conditions, in the United States, we're going to use nominal voltages of 120, 120, 240, 208, 120, 240, 347, 480, 277. There's nickname voltages. And we say we're going to rally behind all these specific voltages. And that really has nothing more to do than tradition and the physical internals of the electrical components, namely the transformers that govern our electric grid. So here we have a 220 volt branch circuit service. This is 120, 240 volt split phase. And so all we have, the reason why we use this 120, 240 volt residential electric service is simply this is the common transformer that the windings inside the transformer are specifically designed to make it, and it's just the standard that we use, and it's how we step down our medium voltage from the power lines that may be operating at 2,400 volts, how we step that down to 240 volts, and then again to the 120 volt circuits inside our home. Now, in our home, we have single pole breakers that are 120 volt circuits, and then we have double pole breakers that occupy 2 breaker slots, and those are for our higher voltage appliances, like maybe your dryer circuit is on a 240 volt device. Maybe a deep freeze might be on a 240 volt device. It'll just take and be designed for a little bit more powerful electricity, electricity that operates at a little bit higher pressure and can push more electrons through a conductor than a 120 volt circuit can. All right, let's study this picture. This is something I definitely was scared of when I got into the solar industry, because often you'll be designing your home and the utility will want you to install the meter box and the masthead and the weatherhead, and even put in conductors all the way up to this point. And then the utility will come along when they establish a new electric service. You have your higher voltage power lines coming in from the utility, and then they pick out a transformer for your electric service. In this case, it's a 240 volt uh, split phase. And what we can see here is that the utilities neutral is actually going into the transformer too. This transformer circuit is grounded at the bottom of this pole. And then the utility conductors come along this wire and then get taped up into the masthead. Now, I've seen situations where the utility has come out during an install and installed the transformer and these power lines ahead of our commissioning, and they taped up the wires that were hot. And I've seen these wires sway in the wind and touch the side of a metal building and cause a ground fault that kind of blew apart some connectors on my grounded solar array. You know, you always have to be aware of what's going on during an interconnection process because these wires are hot. There's no off switch to these power lines at this point. You know, there's a little switch right up here at this fuse. You know, often when the utility wants to simulate a power outage on site, they're going to come in and with a pole and kind of poke this fuse up so that the transformer loses power, and they'll sense a power outage and see that the solar array turns off. This weatherhead is to keep rain out of this service box. You know, if this was up, rainwater could, you know, this drip loop here will prevent rainwater from getting into the meter in the meter box. So then we get to we've talked about what is a neutral conductor. And this says the conductor connected to the neutral point of the system that is intended to carry current under normal conditions. So the neutral conductor is a current carrying conductor. It is intended to carry current. The equipment ground conductor that connects all the metal parts together on your building is not intended to carry current. The neutral conductor is intended to carry current under normal operating conditions. And depending on your transformer, your electric service conductors are going to be slightly different from each other. So here we have a 120 volt single phase, 240 volt single phase, and then 120, 240 volt split phase. And so they are actually all different. A 120, 240 volt split phase is different than a 240 volt where you just have a single leg to ground. A 120 volt service is different than a 240 volt split phase. And then you get into three-phase services, and the windings start to look even more complicated, and they have different terms for it. And it really just depends on the utility, on which transformer they want to install, or what kind of motor you're trying to drive. But there's delta services and Y services, and you know, at any point the neutral wire is supposed to be, you know, it's going to be balancing out and connected to ground at one point. For branch circuits, we're still defining things. So once we get into breaker sizings, we'll better understand the role of the neutral wire. Branch circuit feeders and service calculations, fractions of an ampere. Calculations shall be permitted to be rounded down to the nearest whole amp with decimal fractions smaller than 0.5 dropped. And so you might be brand new to performing calculations, and you know, maybe you took some engineering courses in college where you get the concept of significant digits driven home, and you might try and capture all the significant digits possible so you can carry your voltage and amperage calculations out to the 0.001 level. You know, code is trying to keep the design work. You know, it bridges that gap between the Poindexter and the pragmatic off the shelf product. You can do engineering calculations in code, and maybe engineering calculations even when not mandated, such as there commonly are at higher voltage, over 600 voltage calculations. Maybe doing an engineering calculation and calculating the exact operating conditions can show that you can get away with a smaller conductor size. But generally, in those circumstances, you're going to be, you know, erring on the side of oversizing than undersizing. We see these 25% additional correction factors. We'll see temperature correction factors come into code that are all erring on the side of caution. And so I guess by the by the time we get to the final decimal and rounding the system, they say, all right, you can any decimals of amps, any fractions of amps, just round down. And I don't understand the last part. It says you can round down to the nearest whole amp with decimal fractions smaller than 0.5 dropped. I guess that's referring to if you're doing multiple steps in the calculation, how precise you need to go with your calculations. And you will have specific calculations for every specific kind of power device in code. So especially for your perhaps non-continuous loads like dryers and range stoves, or commonly found loads like lighting loads or receptacle loads, have different rules, as well as separate rules for dwelling units versus non-dwelling units. Like a home where people are living full time is subject to more stringent regulation than, say, a warehouse. But that's so we'll visit some of those special calculations as we get into section 400, which is general equipment, and then again when we get into section 600, which is specialty equipment. It says the minimum load of a feeder is the sum of all the loads determined by Part 2 after any applicable demand factors permitted by Part 3, 4, or 5 of Section 220 are applied. And so we have to go a little bit further into this, but basically, you know, you take your load of your feeder service, and then you have correction factors that you need to apply before you get to your final calculation. If you're adding on a section of a building to an existing installation, you may have different requirements than new construction. You know, what's the minimum circuit size that you have to allow for a dryer or for an outlet? Let's kind of accelerate some of the content along here. Got another definition. The authority having jurisdiction, an organization, office, or individual responsible for enforcing the requirements of a code or standard, or for approving equipment, materials, and installation or procedure. So the authority having jurisdiction has final say over what code is used. Remember, National Electric Code is a private industry standard that is not designed to be a design manual. And so your local authorities have complete power to go beyond electric code in terms of having additional requirements. And what's very common is that your local authority will want to have a disconnect switch on the outside of the building that is a very clear and straightforward and easily to see from a distance disconnect switch. And so they're settling on a knife switch disconnect, and it's not part of National Electric Code. So whenever you're doing any kind of solar design, if you design to National Electric Code, you can still make design errors and fail your inspection, because there may be additional jurisdictional requirements that you have to abide by. And so, where do you go and find what your local jurisdiction is? Well, the Desire website is a good starting point. You can go up and look at the interconnection standards in your area, and usually that will lead you to contact information on who to follow up with to determine who the utility is in your area and what the interconnection requirements are. Back on what are these correction factors when we're sizing our feeder circuits. We have different correction factors for lighting circuits, motors, space heating. Let's just look at space heating as an example. Rather than being calculated at 100%, when managing your energy, the local AHJ can allow feeders and service conductors to have less than 100%, provided the conductors have the ampacity for the load so determined. And so, what this is saying is, there may be areas where if you're employing on-site energy storage, like with a battery bank, that your electric service may be allowed to be undersized. We've seen that happen with electric space heaters. And also we see some undersizing allowances based on, the larger of a usage that you're having. So if you have an apartment complex and you're sizing the utility service to go into the complex, the more homes there are, the more stoves there are inside the home, means that they assume not all of these things are going to be on at the same time. And so you can discount it further if you want to. Again, it's a minimum design standard. So on a home, for your house, where you only have one or two of a common appliance, you get all the way up to a 48 kilowatt service panel, and it's very hard. Even if you go and turn on all the appliances in your home, it's very hard to blow the power in your service panel. But you might have buildings, if everyone's running their air conditioning at the same time, you might get into a whole complex or even a utility distribution circuit, experiencing some overloading and having the main breaker switch when you get into too many discount factors applied. The feeder or service neutral load, the maximum unbalanced load, is the maximum net load between any neutral conductor and any one ungrounded conductor. And so we know that the neutral conductor is a grounded conductor that is intentionally grounded at the point of at one point. We're gonna worry about that later. But it says the maximum unbalanced load of the system, which is the load that is applied to the neutral, is the maximum net load between any neutral conductor and any one ungrounded conductor. And what that means is the neutral needs to be the same size as the ungrounded conductors, your leg 1, sometimes leg 2, or leg 3 of power. And then from beyond that, they say, well, under certain conditions, you can reduce the neutral, and under other conditions, you can't. So as a starting point with your design work, if you don't want to make any mistake, don't undersize the neutral, and what that'll, that then you'll be in the clear. If you do undersize the neutral, you may save a little bit of money, but not as much money as a design mistake. if you want to go ahead and do all of your conduit calculations for a full size neutral, you're not going to have any design changes if, when it comes time to order the material, your supplier comes back and says, well, actually, you usually undersize the neutral in this location, and you decide to do a design change. But if you're just beginning, don't undersize the neutral for now. Optional service load calcs, dwelling units, feeders, and service loads. There are other ways to calculate how much power you need to give to dwelling units. And so what we see here is 10 kilowatts for general service, and then 3 watts a square foot for lighting for 40% of the home. And then for every 20 amp branch circuit, you throw on an additional 1.5 kilowatts. And then you do 100% of the continuous load ratings for, your appliances, cooking equipment, dryers, water heaters, motors, stuff that is your non-continuous loads. And then you have your heating and air conditioning loads. They say, well, you're not using both at the same time. So, what's your maximum load in the spring, or what's your maximum load in the winter between the two pieces of equipment, and design off that. And so there are some, in terms of establishing the minimum service for your home, there are some general rules to go by. And generally, these rules will get you into, a 100 amp service for a small unit, and then 200 amp service for a large unit. It also might mean that if we're generating energy on site and we are managing our energy with a battery bank, that some of our home electric services are going to start to look pretty oversized compared to, if you're an energy efficient home and you're fine tuning your energy use. You might find that your home is only using 60 amps of power, but you have a 200 amp electric service. Um, let's see. So, how do you determine your existing loads? You're actually allowed on existing constructions to base your load calculations off of real monitored usage. And so, you generally will use a 1 year period of load. And if you don't have 1 year, you base the maximum 15-minute demand using the highest air conditioning or heating load over the past 30 days. Now, where this is relevant to on site power systems is sometimes your utility will establish a maximum size that you are allowed to interconnect to the grid based on your 1 year load usage. And, I've heard that, it's kind of interesting. You go to net metering, they say, well, you can't have a system that will offset more than 100% of your energy use. But I've also seen requirements where they also say you can't do an array that will offset substantially more than your power. So I had a client who wanted to do a 50 kilowatt array, and he had, that would be like on a 40 kilowatt inverter, and he has a 48 kilowatt electric service, 200 amps times 240 volts. A volt times an amp is 48 kilowatts. And so he wants to max out his service connection and do the largest possible array he can, and just sell back a lot of the electricity to the grid at wholesale pricing. And the utility comes back to him, and they say, you don't have the load to accommodate a 48 kilowatt array. And so before they go and review that, before that process comes in, you may actually want to go around and turn on all the circuits in your home at the hottest time of the day for a 30-minute window under a residential service, just so that you can spike your load all the way up to its maximum, so that when the utility reviews your electric use, they can't come back and say, well, your load doesn't get anywhere above 16 kilowatts, so a 48 kilowatt array is way oversized for your use. You know, you may there may be some reasons for you to go and juice your demand so that you can not just reduce the minimum service size, that the minimum that needs to be established. There may be reasons to go and go way beyond that and go up to the maximum service size. And maybe you want to qualify for a demand rate structure because you have a battery bank. And the utility might say, well, we only do that for homes that have X amount of demand. So you might want to go prove that you can have that amount, and then and then take it from there. Okay, so it is 12:40. We or 12:37. We have been at this now for an hour, a little bit over an hour and a half. So it's 12:37. Why don't we take a 15-minute break? And then when we pick up, and so what we'll do is we'll pick back up at about 12:50 Central Time. So about 1:50, little past 1:50 Eastern Time. We'll pick back up from our break and keep slogging through section 200 and then get into section 300. But just remember that section 200 and 300 are establishing the ground rules, and if we understand these concepts, then these are the parts of code that are most relevant to all of your electric service calculations. So, we're going to be slogging through 200 and 300 today, and then getting more into the specialty requirements discussion tomorrow. So we'll take a 15-minute break. See y'all in about 13 minutes or so at about 10 till. five. Five. Nice.
Just good to be home. I was listening a little bit, but I figured it might throw it off. So I turned it off, but it sounds really good.
Yeah, I think so.
You don't sound like you're having any problems.
It's just very basic.
Well, that's alright.
They still get their credit either way.
No, but I mean, are they saying, like, can you go faster? We already know this stuff? No. So then, whatever. If they record, they tell you. Right?
Right.
And I mean, you have to go through the boring stuff. It's not going to get more exciting.
Yeah.
And it can be basic because it should be.
Right.
If you can't explain something simply, then you can't. Then you don't know what you're talking about.
I'm gonna surprise them after the break. We're gonna cut away from it. Go do something interesting. That's nice of Bubba.
Oh yeah, I told him he said, how was Labor Day? And I'm like, we're really glad to meet him. My friend's like, he's gonna be so happy to sit outside with you later. And just relax.
Yeah.
Yeah. I'm struggling. You really need to work on my computer. I just got it out. I'm a million places to work right now. I want everything to be
All right, we're gonna pick back up in about 1 minute or so. So this is the 1 minute warning, and then we'll get back down to business. All, all right, so welcome back. Uh, as we're getting back into class, we're gonna dive right back into section 200 and keep slogging through. So this is just that kind of course content. But before we do that, let me distract you with something a little bit more entertaining. What I want to show you is what solar installers would do to generate a national electric code report. And this is only going to take about 2 or 3 minutes. It uses a solar design software, but this design software is free to use. It's just if you want to save your content, it is that's when you have to sign up for it. And I don't want to get too much into software training as we're not really allowed to do that. So let me just quickly get through this. And the reason why I want to illustrate it is to say, why don't we go ahead and use Half Moon's Half Moon's address. So what we're going to do is just do a real quick array layout sketch on Half Moon's facility and generate a national electric code report for it. So their address is 754 Bartlett Avenue, Altoona, Wisconsin. And let's see. So here's we're going to define our roof space. And they're on a 412 roof pitch. The array faces south. And then let's just go ahead and save roof. Let's go back to the roof face and define the boundaries. This is where I would pull up, say, Google Earth. We do this in other classes and get more into the detail of it in the Design Your Solar Roof course. But we're only going to focus on the National Electric Code report for this exercise. So here's Half Moon's rooftop. And let's just assume for the simplicity purpose that they're a perfect rectangle that is about 106 feet long by about 23 feet deep, just for brevity's sake. So 106 by 24. And we're not going to go and add any obstructions or anything like that. And Half Moons was a microinverter array using a 250 watt panel. So let's just go ahead and pick out. Here's a 245 watt panel. No, no worries on that. And here's a in-phase microinverter. So this might not have been the exact system we did a few years back. And then let's go and put in our fire code clearances of 3 feet off the rake and 3 feet off the ridge. And since we're talking about code class, there are other parts of code beyond National Electric Code. Like for those who are here for the NABCEP continuing education, you're well familiar with the 3-foot offset rules, 3 feet off the sides of the roof, 3 feet off the top of the roof. And that's when there is no forced air ventilation system to ventilate smoke during a fire out of the attic. If you don't have a forced air ventilation system, you have to have clearances on your rooftop for fireman access. And that's not part of National Electric Code. It's still part of code. There's National Fire Code, of which Electric Code is just a subset of it. And anyway, so we're just covering National Electric Code, but there's 3 feet offsets. Let's just quickly build out some microinverter circuits. We'll just do let's see here. Can I make this small? Don't know how to make that any. There we go. All right, so we'll do 17 and then 17. Why don't we just go ahead and make that try 14 and 14? So we'll do a 15 circuit and a 14 circuit, another 15 circuit, another 14 circuit, another 15 circuit, another 14 circuit. And so that's our solar array. And we could go and fine tune it further. So I just want to get to the National Electric Code document. So here we are with our balance of system components. And we'll say, okay, well, we're transitioning at the array into the attic. And the question is, well, why is that important? What's the difference between being up on the rooftop and being inside the attic? Well, we've seen that there's the roof is a wet condition and the attic is a dry condition. And furthermore, there's another part of code that says, hey, if there's moisture in the air outside your house and then you have a drier air conditioned space inside the house, that difference in moisture alone is going to cause the higher pressure moist air to be kind of going into that conduit and then condensing. And where's the water going to go? It's going to drop down the conduit. And so you have to seal conduit going into the roof, into the attic with a little sealant that you spray. Also, underground conduit coming up from the ground into a dry space or into the attic. I've seen a cabin with underground feeders coming up where it's just between the underground feeders and the cold shaded concrete to the atmosphere in the south where it's hot and humid outside. You open up the tap line side tap box and there's a puddle of water inside what you think should be a NEMA 3R weather rated box. And that's just because the humidity alone can cause it to rain inside your equipment. And so even though it's a weatherproof box, you still may need to install a weep hole inside the box to get the moisture out of there. So anyway, to answer all questions of electric code, we're saying, okay, well, we're going into the attic at this point. Let's say we're doing a supply side connection. Do we want to use a fused disconnect or a breaker box? Well, now we know that either one is a main overcurrent protection device. And so why don't we just go ahead and use a breaker box since we have multiple microinverter circuits and our grounding system, let's say we're using a grounding system with racking where the grounding is built into the racking itself. Then we get into wire and conduit options, and this stuff is Greek to me. Uh, when we get into National Electric Code conductor selection, there's going to be all these acronyms, and you don't know what the acronyms stand for without industry experience. But what they stand for are the temperature ratings and the environmental condition ratings, and whether it's a wet or dry environment, and the voltage ratings for that matter. Is it a 240 volt or 300 volt cable? Is it a 600 volt cable? Is it a 2000 volt cable? And so we see in this particular solar design software, we see a survey where it's already, it's saying out of these three cables, which do you want to use? And what this is telling me is if I have no clue what cable to select for my system, it's telling me that these are common cable types to select. And what we'll learn later is the W in these cable types refers to a wet condition. And that little -2 refers to a sunlight resistant rating. And it turns out that all of these cables are rated for an appropriate voltage to be outdoors in a wet environment in exposure to sunlight. What I'm trying to say is if you're, as a learning tool, solar design software can kind of coach you in the right direction towards code compliant design. I used to be afraid of this stuff that it would make a mistake and not have something in it that was important to code. We'll be covering those sections, coming through those sections, but it does make a useful guide. So anyway, then we get to our branch circuits and we see there's questions about, well, how close is the conductor to the rooftop? Well, there's different temperature derating requirements that have actually changed in NEC 2017. There's a substantial temperature derate for being from 0 to 0.5 inches above the roof, and this middle range from 0.5 to 3.5 has kind of gone by the wayside. But in 2014, there's different temperature ratings for these different levels. So anyway, we're going through the building interior, then to the utility disconnect and breaker box output. We'll just go through the building interior. Then we get into our voltage drops, and these are our links of the building. So going back to Google Earth, let's just assume our branch circuits are running 55 feet, and then to the point of interconnection, that's 27 feet, and then maybe 15 feet down from there, plus slack. The worst case scenario, we're looking at 50, 80, 90, about 100 feet here for our branch circuits. And this is going to have a really good reward at the end. Transition box to the sub panel. Our 6 branch circuits, microinverter branch circuits, are going down to the building. The combined output of the inverters to the sub panel, that point of interconnection is going to be pretty close. So we provided some more site information that has to do with code. And now it's calculating our conductor sizing. And, you can't rely on software alone, but then again, it does make a heck of a guess, like as a guidance. Like that in-phase microinverter cable is number 12 AWG. And it has a little bounce of system box that only takes number 12 AWG. And so what I'm seeing is it's all right. It's within range to do number 12. And then I'm in number 2 when these things combine. I'm looking at my conduit. It's all half an inch, then inch and a quarter. You know, all this stuff is fine. And where the payoff is with this particular software, which again, you know, you could be doing this now along in class if you want to. It's just, it's free to use. It's just if you want an account, you save your work, you got to pay for it. It makes a great tutoring tool. Now what we have is a let's see. What we need is to export the code report and the payoff that I really wanted to illustrate here, you know, in other classes we go into the one-line diagram that may be contained in this or not. But in this course, what I want to highlight is, you know, right now we're doing a start to finish read through of all the nits and bits of National Electric Code. But if you want to cut to the chase and start with the calculations that are most relevant to solar design, your solar design software can guide you on that. So here we have National Electric Code references where, you know, you can't exceed 600 volts. And it goes into the voltage calculation for Article 690.7. And that's the solar specific section of 690. And hey, look, here's the ASHRAE database temperature. So that's pretty useful. Well, then on top of that, we get into the current calculations. Like, what is the continuous current of a solar array? Well, it says we have 14 microinverters at 0.9 amps each, and so it's 12.6 for the output current circuit of those inverters. Then we look at the based on what wire selection we've used, it runs the calculations for you and gives you what those calculations are. And so, you know, this is calculating the taking into account the 75C terminal that we talked about earlier. As we get into the next sections for the rest of the day, we're going to be getting into overcurrent protection device and equipment ground conductor sizing. And this report has all of those calculations as well as code references. You know, here's 240.4D, which we haven't gotten to yet. And then we have those calculations for every branch circuit on the rooftop. And now we're, you know, what we need to do is get down to the, not from the circuit to the combiner, but now we're at the main service panel to the point of connection where we've transitioned into the number 2 copper. And what we see is that our equipment ground conductor is undersized. And we see our conduit sizing. And what we'll see in the next couple of sections of code under the general sections, that's all in sections 2 and 300, 400. So we have, it's getting into the 90C conductor derate factor, the fill factor, the output ampacity adjusted for temperature and conductor fill. Getting into the table 250, which we haven't gotten to yet, which is the equipment ground conductor sizing of number 8. And then also getting into things like conduit fill calculations as well. And I guess this is, I'm not sure if it's referencing the table or not, but we'll see it in a bit. And so what I'm trying to do right now is just to show you, hey, we need to get familiar with these terms and talk about what is not necessarily in the code reports that the solar design software gives you. I also wanted to show you how you take this knowledge the next step and create these reports for your own job site. So I don't know. I reading off slides needed to do something a little bit more useful. Now let's get back into the discussion. All right, so we have a building, which is a structure that stands alone or that is cut off from adjoining structures by firewalls with all openings therein protected by approved fire doors. So, a building is a standalone structure or a structure separated by firewalls. And so the question is, well, you might get into an issue where is the equipment, like, is a ground mounted solar array considered to be on a building or not? Now, there's different requirements for if this is on a building, you have to do rapid shutdown. If it's not on a building, you don't need to do rapid shutdown. And so, while I think it's smart on ground mounts to do rapid shutdown combiner boxes, at a utility scale project where money's the bottom line, you may not have that feature. You may not be required to have that feature. Well, it depends on where you locate the equipment. If the inverter is mounted on the building wall, that's considered to be on a building. Maybe your local jurisdiction will let that slide, maybe they won't. What's the difference between a building and a garage? A garage is a portion of a building where vehicles are kept. So a garage is still considered to be a building and it's not exempt from code simply because it's a garage. It's just that there may be different code requirements for dwelling units rather than garages that don't have any dwelling that goes on inside them unless they're attached to a dwelling unit. Bonding, connected to establish electrical continuity and conductivity. So the question is, well, what's the difference between bonding and grounding? And the answer is there is not much difference. Bonding is concurrent flow between two things, and all of your metal parts are bonded together, and all of your metal parts are attached to that equipment grounding conductor. So, whether or not you say the metal is bonded to the equipment ground conductor or the all metal parts are grounded, I guess saying that the metal is bonded to the equipment ground conductor is more specific than just saying all the equipment is grounded, because that gets confusing. It's like the neutral is grounded at one point, but the equipment, the metal shells are bonded not to the neutral. The metal shells are bonded to the equipment ground conductor. Well, and then you have a bonding jumper system, which says the connection between the grounded circuit conductor, that's a circuit that is intentionally connected to ground. The connection between the grounded circuit conductor and the supply side bonding jumper or the equipment ground conductor or both at a separately derived system. So what the heck does that mean? It's wherever the neutral, the grounded conductor at one point is connected to ground, and whether it connects to the equipment ground conductor for the entire system. Well, anyway, sometimes we're gonna come back to where the bonding jumper system is located. But what I want you to think about right now is that all of the metal parts on your systems must be bonded together. Now, there's different requirements for when you're under 250 volts and over 250 volts. But, basically, when we're talking about solar power and on-site energy management systems, you need to ground all metal parts, and you'll make mistakes when metal parts that you think don't need to be grounded do actually need to be grounded. All your metal parts and your battery systems, etc., need to be grounded. And so you might have your solar rail that is metal, and your modules are connected to your solar rail, but that doesn't necessarily mean they have the electrical connectivity. They need to conduct electricity, and metal has, whenever it has a like an anodized finish on it, that, instead of being a raw piece of metal, they coat it, and they coat it for corrosion resistance, they coat it for aesthetic purposes, and that coating eliminates the conductivity. And so you have to have, what we see down in the middle lower picture is a grounding washer between two pieces of rail. Now there's a stick of metal, right smack dab in the middle of these two pieces of rail, and that piece of metal is there to splice the rails together and turn them into one rigid piece of rail instead of two separate pieces of rail. But that splice is not listed as a ground path. And so here we have a separate bonding jumper that bonds the two pieces of rail together. And so that's another thing, is just because it's metal touching metal, that doesn't mean that it's actually qualifies as a ground path. Piles that are driven directly into the ground, you think, well, the ground is the ground, and that's metal going into the ground, but it may not have enough resistance to qualify as a ground path. Two pieces of anodized metal racking being pressed together does not qualify as a ground path. Grounding the racking system directly to a metal rooftop may not qualify as a ground path. So ignore the where's the bonding jumper system at this time, because it's not on, the bonding jumper system is not shown on this picture. The bonding jumper system is not shown on this picture either. We'll come back to it. And then we get another definition: an enclosed assemblage of equipment, switches, circuit breakers, buses, and transformers under the control of qualified persons, through which electric energy is passed for the purpose of switching or modifying its characteristics. Now that's what these substations will take your high voltage lines that are coming from the power plant and then convert that into medium voltage that'll go out to your communities. And then there'll be another medium voltage conversion that'll step it down to your distribution circuits, and then another transformer conversion that steps it down to your power lines that come into your home, which are your 240 volt split phase, or 208 three phase, or 208 delta, 208Y. So we have these outside branch circuits and feeders that are on or between building structures or poles. Equipment and wires for supply equipment outside of buildings. Then we get into table 225.3, which is really more of the table of contents of the National Electric Code that tells you, there's all these other special equipment rules and considerations. Special rules for branch circuits, special rules for communication, fire alarm systems, de-icing and snow melt systems, all of these, boat docks. You want to design a floating solar array. Well, there's a section of National Electric Code out there that governs floating buildings. So there are specific rules for specific applications of electrical devices within code. A new definition, raceway, an enclosed channel of metal or non-metallic materials designed expressly for holding wires, cables, or bus bars with additional functions as permitted in this code. And the key word here in raceway is enclosed. And the definition of enclosed is surrounded by a case, housing, fence, or wall that prevents persons from accidentally contacting energized parts. And so the issue is you might have a, let's say you want to do building integrated solar where you have a house, and rather than putting the modules onto the rooftop, you actually want to make the roof out of the solar modules themselves. And so you're building your rafters, and let's say you do some glass on glass solar modules. And so you have glass on glass solar modules, and that's pretty nice because that's nice and well insulated, as far as the interior of your building. But so here's your rafters, and you're putting down your glass on glass modules, and you're using like butyl skyscraper glue to seal the glass together. And that's something that, more of a building framer will be better suited to do. So here's your rafter. Here's your solar panel. And that's what we say in the solar panel design and development class, is that some of this stuff like building integrated solar you can do with the existing products that are out there on the market. It's just that the solar designer out there isn't interested in doing that high level stuff. They just want to do the put it on the roof, sell the system, get on to the next project site. It may be up to the architect or the general contractor to go and do more of these high-end designs, because then it's more just a regular plain old high-end luxury home project, not an economic bottom priced solar array. But the problem with building integrated solar is more that now you have these cables coming off the underside of the module. And what we'll see a bit later is direct current circuits must be in an enclosed metal raceway. And so the question is, if you have these exposed circuit conductors that are not fully enclosed in a metal raceway, then you're just asking for a code violation. If you have DC conductors coming off the back of the module and they're inside the home, they must be in a metal raceway. But if they're not in that metal raceway, then how do we enclose them in a metal raceway? You might get a nitpicky inspector that would fail you unless you identify that, hey, we're going into the metal raceway as soon as we can in this system, but that might mean there might be a half an inch of space. And so you want to point this stuff out during the design process to the AHJ so that you can do your fancy building integrated solar projects, and not do them and then have a very authoritarian inspector show up and say, that's a DC conductor and it's not fully enclosed. That's a code violation. Ground fault, an unintentional electrical conducting connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors of metallic enclosures, metallic raceways, metallic equipment, or earth. In other words, whenever you have an ungrounded conductor, that's a conductor at high voltage. It's not connected to ground. It's not connected to zero voltage. So you don't have high voltage flowing into a low voltage state. It's a high voltage power line. And then it connects to that non-current carrying metal conductor. And it faults. And that current connects to ground. And that might sound like, oh no, there's something wrong. And there is. A ground fault that is not planned for nor expected is not a good thing. But what would be worse is for that ground fault not to occur and for that metal box or that metal conduit on the building to be energized, and you go up and touch it and you become the ground path. And that's even worse. Right? So when we do have ground faults, we need to have a path to ground for that ground fault to carry over. And then we have the ground fault circuit interrupter, a device intended for the protection of personnel that functions to de-energize a circuit or a portion of a circuit within an established period of time when a current to ground exceeds the value established for the device. So what happens during a ground fault? Now you get this high voltage flowing into this low voltage, and if the power's on during that time and you always had that supply of high voltage, then it's like a waterfall of current that's falling out of the wire as quickly as it can into ground, and it gets so much current that it could heat up and start a fire. And so we have a ground fault circuit interrupter that can detect when a ground fault is occurring and then lift the breaker up in the service panel, de-energize the equipment, and interrupt the ground fault. Then we have an arc fault current interrupter, which is a device intended to provide protection from the effects of arc faults by recognizing yada yada. Arc faults are different than ground faults. Ground faults are when the electricity goes from that ungrounded conductor, that high voltage conductor, and it touches a low voltage component, like a metal part that has no voltage on it, and it's connected to the equipment ground conductor, and the power spills over into the EGG and flips the breaker on your panel. Arc faults are different. Arc faults are like if you imagine you take a power plug, and I do not, don't do this, just imagine it. Let's say you have an extension cable connecting a generator to a load, and you're daisy chaining extension cables together, one after the other, and you take that extension cable and you under load, you try and pull it apart. Then that's very dangerous, but in the cartoon version, you might imagine this arc of electricity going between the male and female lead as you try and pull it apart. And in a solar array, where that kind of fault might occur is in the module to module connectors. What they're called are MC4 connectors. So let me pull this up. MC4 connector. So these are MC4 connectors, and they form the module to module connection, and then at the end of a circuit you build a custom MC4 connector, and you run it all the way back to where your inverter is. And usually the module to module MC4 connectors are of high quality and compatible. But the problem is, even though a variety of MC4 manufacturers make these MC4 connectors, when you go from module to module, it's the same manufacturer providing the MC4 connector of both sides. But when you get out into the field, you source your MC4 connectors from a third party, and there's quality differences. And so while they all are standard and match up together, there is a quality difference between high MC4 connectors and low MC4 connectors. And it's not just a manufacturer quality, it's a workmanship quality of how well, you let me clear my mess here. You run a conductor through the end of this and into this metal housing, and then you crimp the housing, and you have to snap it into this conductor, and then this piece twists and kind of rotates, and you have to make it up tight, otherwise it doesn't connect the cable to the pin. And so there's when you're making up the MC4 connector in the field, there's a number of spots that can go wrong. And lo and behold, my experience is it's the MC4 connector that is the most common point of failure. And so you have a poorly made up MC4 connector, and rather than connect to ground, it's just you have a positive and negative side of your cable, and every so often either current doesn't flow or you get electricity arcing and still flowing, but that can produce heat and smolder a cable and start a fire, and that's obviously dangerous. And so National Electric Code over time has, it used to be that it just required ground fault protection and ground fault circuit interrupters. Nowadays, the inverters have arc fault detection in them as well. And that's produced kind of a phenomenon where owners of older systems think that solar arrays are bulletproof and nothing ever goes wrong with them, whereas you install a newer inverter with the arc fault detection and it recognizes when that MC4 connector is not made up correctly but still operational, and it shuts off. So that's for the best, but it's also showing you that older legacy components, eventually should be upgraded to the latest iteration of code. In fact, in your old school central inverters, the way that their ground fault detection circuit was intentionally grounded, it's called a grounded inverter, and it really has to do with the ground fault detection and how the DC side ground fault detection detects ground faults. Does it reference a voltage to ground, or does it monitor that voltage in a different manner? Is it a grounded or an ungrounded inverter? And in grounded inverters, when you have multiple strings, there's a blind spot in the old school central grounded inverters on commercial systems that has burned a couple buildings to the ground. I guess that's a bad pun. So anyway, there's ways that we can reduce these ground faults. For ground faulting, generally you don't want to make your circuits unnecessarily long. Um, you if you to reduce ground faults anywhere where your circuits can be dragging across a hard surface or against a surface that has a jagged edge on it, such as where a conductor meets or a conduit meets another conduit. All of that could expansion fittings that don't work, can cause a problem. If you keep your array subsection small enough such that thermal coefficient of expansion is no longer necessary, then you get less of a need for expansion fittings. There's fire code that says on commercial buildings every 150 feet you got to put a walkway for fireman access. And then you think, well, if I'm using a forced ventilation system, do I need to do that? Well, there's other reasons why rooftop clearance requirements on your solar array are worthwhile. It's not just about fireman safety, but having smaller subarray sections reduces thermal expansion. On top of that, your wind loading. You get, if you stay off the edges of your rooftop, your solar array has less wind loading. And so structurally, it's better to stick to the interior of your roof. Arc faulting, it's more about, are your connectors made up tight and correctly? And then avoiding fine strand conductors, but you don't use fine strand. You use stranded conductors in solar, but it's not fine stranded. Article 225, outside branch circuits and feeders, wiring on buildings. The install of outside wiring on surfaces of buildings shall be permitted for circuits under 600 volts nominal. And let's see. And then it lists out different ways that you can have wiring on buildings. So you think, well, can I just go and staple a wire to the edge of the building? Code has a list of ways you can do it. You can have wire in metal conduit, wire in PVC conduit, wire in cable trays, and even certain cables that we'll get into in section 300 have protection and support built into them. And so if you see just a random cable running up the edge of a building, either it's the system ground, or it's a special cable that probably has a harder shell around the exterior of it. Outside branch circuits, where outside branch and feeder circuits leave or enter a building, there are some restrictions that are further on down into code. Support spacings. This 225.12 will govern what the distance is between straps, what the distance is between putting little neoprene support blocks or rubber pad support blocks underneath your conduit as you run across a flat roof. As you go up the rooftop, because of the weight of the cable that is just hanging in the conduit. And where does that weight go? Well, it goes into the conduit. And so every so often you need to strap that conduit onto the wall and transfer your load, into the wall, the support wall of the building. All of these things are picked up in code. Well, for that matter, the solar design software only goes so far. The furthest that I see solar design software going into the industry is what we just saw, where it gets into conduit sizing and conductor sizing. But I don't see any industry software going all the way into calculating all the straps and all the rubber support blocks that you need. And so if you're unfamiliar with code, this is a great this is where like the scope handoff would occur between, the designer and the general contractor. The designer and the installer who's pulling the permit and performing presumably a design review. Supports over buildings, attachments to buildings using masts as support, clearance for overhead conductors and cables, and there's different scenarios for going between from 10 feet up to 18 feet of clearance requirements. This is where, going back a few slides into the the crow's nest, or the weatherhead on, well, how tall up does this weatherhead need to be for these power lines from the utility to just drop down and be taped up? And these are overhead wires, so how tall up does this need to be? Well, right hidden in the very beginnings of code, where we're still talking about feeder circuits supplying power to a service panel, that's where that is. Often it'll be a 18-foot clearance. Clearances from buildings for conductors not over 600 volts, above rooftops, 8 feet above the roof, or not less than 3 feet away from the roof in all directions, except when the roof is subject to pedestrian traffic. So if there's a rooftop deck, if you have a overhead power line going across your rooftop deck, that may need to be 18 feet high instead of 8 feet high. The final span, eventually these wires have to go into the building. So the final span between your wires in the building should be 3 feet away from windows and doors and porches and balconies and ladders. If you have someone who's going to hang 3 feet out a window and grab onto a power line, not much you can do in that situation. But then again, if your power line is, you have a 3-story tall row home and your power lines just go up to the top of the home, uh, you're running your service conductors from the power line to the house. It's only on that top span at the very top of the unit where you can get closer to the window to stay just on the top edge of presumably an inaccessible rooftop. So the final span, you have to stay 3 feet away from your windows and porches and balconies and ladders, unless you're at the top level of the home, at which point you can just go above the window, between the window and the top of the building wall. And then conductors on buildings, structures, or poles require mechanical protection, subject to requirements that we still have to get to. Multi-conductor cables on exterior surfaces have different requirements. Raceways, the main thing about raceways on the exterior of buildings is that they need to be arranged to drain and be suitable for use in wet conditions. So, in other words, you might have your wires coming out of your array into a box or into the roof itself. You might be going from a box into the roof. Well, you don't want to arrange your wires and conduit such that, let's say you put the box at the bottom of the rooftop instead of the top of the roof. If your entry point is at the bottom of the rooftop, it could be that the water is flowing down the roof and then it might run into the box. And I've seen this before on actually it was on Half Moon's rooftop. We put a pipe boot on a large piece of conduit and ran it into a PVC box. And there are a few things that did not get done on that box. And what happened in this case was it was the combination of a heavy rain is when they noticed the water coming into the rooftop, and the contractor had not sealed the inside of the conduit. And so what happened was the water was pouring down into the box and actually getting up into the box. The fault was that while the pipe was in a pipe boot, the contractor did not put additional sealant between the pipe boot and the fitting inside the box. So water was getting into the box and then falling through the conduit into the attic. That was not arranged to drain. If we had instead taken that box and located it up to the top of the rooftop, you wouldn't get the water running down the edges of the conduit into the internals. So you have to think about drainage, and then again we've talked about raceway seals as well. Where a raceway enters a building or structure from underground, it should be sealed. Spare or unused raceways should be sealed. Sealants should be identified to use for use. So you have to use listed sealants. You can buy these things at your local hardware store. Then we get into the number of supplies. So a building or structure that is served by branch circuits or feeders on the load side of a service disconnect means shall be supplied by only one feeder or branch circuit, unless there are special conditions or special occupancies where the space constraints make it untenable. And so this is kind of interesting. It's referred to as the 6-handle rule. What that says, a building or structure served by a feeder circuit on the load side of a service disconnecting means shall be supplied by only one feeder or branch circuit, unless you have a separate power system for fire pumps or emergency systems, or you have on-site power resources like solar or generators or standby. So what that says is you should not have two utility services feeding the same building for no reason. Just because you want power on that side of the building and the other side of the building. The building has to have the one supply unless there's a special reason or special condition for it to have two. Then again, supplies only go up to be so powerful, and so you're allowed to add additional supplies to a building when you're at a supply voltage of 600 volts or less in excess of 2000 amps. So let's say you're a commercial array building and you're on a 480 volt service and you have 2000 amps of service. That's around 10 to 15 megawatts of power. And if you are an on-site manufacturer and you need even more power than that, once you get up into those higher levels, they give you the ability to get special permission to have multiple services feeding the same, I guess, building. Disconnecting means shall be provided for disconnecting all ungrounded conductors that supply or pass through a building or structure. And so if you are penetrating through a building between your generator and your battery bank, or your generator and your service wall, or your solar array and then into your building, there needs to be a disconnect. And in the past, this disconnect requirement has been very confusing because there's also the utility disconnect, which really, when it boils down to it, it says it can be located outside the building or inside at the first available spot. Really what utilities want is they want a disconnect on the side of the building that they can use to turn off your on-site power systems. And maybe that'll be multiple disconnects for when you get into having a solar array and a electric charging vehicle station, something like that. Does there need to be a disconnect up on the rooftop? It says you need to have disconnecting means for disconnecting all ungrounded conductors that supply or pass through a building or structure. And actually, we get into rapid shutdown, and what we realize is that in the past, we've just taken the conductors from the array and fed them directly into the string inverter, and installers have been kind of getting around the spirit of this by staying outside the building, and they're not passing through the building. But as installers get more experience, they say, well, I want to keep the conductors inside the building for a few reasons. If it's inside the building, A, it looks good. And to sell residential arrays, you got to make it look good to be in the business over the long-term value is what we're talking about. When you're inside the array, it's not exposed to the weather. You get some really mean squirrels out there that can, So when you go into the roof, there's actually a box up on the rooftop that doesn't always disconnect, but can disconnect. It's part of your rapid shutdown system. Location. The disconnect shall be installed either inside or outside the building where the conductors pass through the building. The disconnecting means shall be at a readily accessible location nearest the point of entrance of the conductors. For the purposes of this section, the requirements in 230.6 shall be utilized. Well, now we have some new definitions to talk about. The first is what is accessible, and then what is readily accessible. So accessible is that the device can be easily approached. Readily accessible is a little bit different. It's being quickly approached. And the spirit of readily accessible is essentially without requiring people to grab a tool. So to grab a ladder or something like that to get access to that disconnect. So you don't have to climb over obstacles. And so accessible means that you can get to it, But readily accessible means you cannot use any tools other than perhaps a key to open up the accessible device. So something that is permanently enclosed into the building facade would not be considered accessible. And then there's also a definition of in sight from, which is typically where you can see it from point A to point B, and it's not greater than 50 feet. Definition of disconnecting means being means shall be provided for disconnecting all ungrounded conductors that supply or pass through a building or structure. So the question is, does your disconnect need to disconnect the neutral? The answer is no. In fact, sometimes you should not disconnect the neutral. For instance, if you want to have a autonomous relay, an automatic relay between your utility and your transfer switch and your on-site generator and your solar array and your battery bank, where you want when the power goes out, you want the switch to flip and you want to go on to your battery bank, and then you want the generator to turn on when your batteries deplete, but then when the power comes back on, you want to switch back on to grid power, and you want it all to happen automatically. Well, you may need to have a neutral be fully connected throughout the entire system in order for that kind of automation to occur, so that you can monitor the status of the grid versus the status of your generator versus the status of your battery bank. The disconnecting means shall be at a readily accessible location at the nearest point of entrance to the conductors. Well, is a rooftop readily accessible? No, you need a ladder to get up onto it. And so what we're talking about for this disconnecting means is really, the utility is looking at that knife switch disconnect on the edge of the building as the system disconnect, or the main solar array disconnect. The disconnect up on your rooftop in your rapid shutdown, that's considered an additional disconnect. And so the readily accessible requirement doesn't apply for whatever reason. Finally, we get to another disconnect rule, the maximum number of disconnects. This is known as the 6-handle rule. And it says the disconnecting means for each supply permitted by 225.30 shall consist of not more than 6 switches or 6 circuit breakers mounted in a single enclosure. Well, what does that mean? Well, we know what an enclosure of switches are. It's our electric service panel. And so what it says is, here's an electric service panel, and it has 6 switches on it, and it's being fed by a supply, and let's say that's our supply coming in from the top. The disconnecting means for each supply shall consist of not more than 6 switches. And so what that says is, if I have and this the reason why I'm having trouble explaining this rule is because let me approach it from a solar design perspective. Let's say let's just go back to our half moon array. So on our half moon array, we had 4 solar panels coming in. And so solar panel 1 lands here, solar array 2 lands here, solar array here, 3, solar array here, number 4. So am I allowed to put all of these supplies onto this one panel and then connect it to the grid? And the answer is yes. I can do up to 6 switches on a single supply. Now, what happens if I have 7 inverters or microinverter branch circuits or what have you onto this panel? And so now I no longer have 6 switches, I have 7 switches. Well, at that point, you put in a main breaker, and that becomes your single switch disconnect switch. Or alternately, you put in a knife switch disconnect with a fuse, and that would serve in lieu of the main breaker. But in either case, you have your main overcurrent protection device and switch where you can flick no more than 6 switches to fully de-energize that supply. So then we get to the grouping of the disconnects, and this is one that stuck out at me. Each disconnect should be marked, and then they need to be grouped. So those 6 disconnect switches, whether it's 6 breakers on a panel or 6 individual knife switches with their individual fuses, they have to be grouped together in the same location. And so you can't just have 3 microinverter circuits on a panel and 3 microinverter circuits on a panel on the other side of the building, both coming in to lugging on to the utility meter inside the main service panel. They would have to be on their individual disconnect switches right by the main service panel, no more than 6 of them. Okay, well then there are reasons for additional disconnecting means, and that would be for your emergency backup systems or even your standby systems. And so here's the problem. Let's say the fire department shows up and they want to power down the building before they go inside. They should not have to flick more than 6 switches to de-energize the building. And so they get there and they flick all the switches. Well, what if one of those switches powers the respirators? And so by flicking that switch, the hospital loses its emergency backup power, and all of a sudden their patients undergo cardiac arrest or whatever. And so standby switches and remote and emergency switches should be located remotely from the disconnect means for the normal supply. But then again, at the residential level, if the house is on fire, the fire department shows up, they don't want to turn the building off only to trigger the emergency power system. And usually with a generator, it's very obvious to the firemen that there's a generator on site. They can just run over to the generator and turn off the generator disconnect as well. But what that means is when you get to where's the disconnect on your battery system, on a grid connected battery, is that disconnect going to be located remotely, or is it going to be located right next to all the other services? I think we're really splitting hairs here. As long as you have no more than 6 switches grouped in one location, and it's all related to power supply, you're going to be fine. If you have a standby system where it doesn't really matter if it gets turned off or not, you don't need to worry about it too much either. But if you're designing an emergency backup system where there are critical loads that must remain energized, even when the fire department is trying to purposefully power down the building, those switches need to be separate from the normal power supply to indicate to the fire department that they're there. Now, also, those switches need to be grouped in the same location. And so what that means is you can actually have 6 normal grid connected solar power switches, or your utility main, and 5 line side connected solar arrays as well, all grouped together. And then you can have 6 additional switches for various battery banks on the outside of the building, for various battery banks and generators for your backup power systems. Identification. So where a building or structure has any combination of feeders, a permanent plaque or directory should be installed at each disconnect location, denoting all other service feeders supplying or passing through the building, with exceptions for multiple connected dwelling units or industrial buildings. Um, and so what that means is when do you have a combination of feeders? Well, we learned that feeder circuits are your utility service, and also feeder circuits are your solar array circuits. So whenever you have circuits from your solar array and circuits from your feeders, a plaque should be installed denoting that there are multiple feeders on the job site. Um, and you may even need to have a map of that location, depending, not just a call out, depending on the voltage of the system. So what can these disconnects look like? You know, when I go and I to the solar conferences and I look at battery inverters, the battery inverter companies are very pleased to show off their motorized breaker switches. The answer is, well, what do you need a motorized breaker for? And at first glance, it seems kind of neat, because if you need to disconnect something for some reason, let's say you have a battery bank and you want to turn your air conditioner off so that you avoid some peak load. You know, you could press a button and motorize that breaker to disconnect your air conditioner, and then when you're out of that peak time, you can press the button and close the breaker again. And those motorized breakers right now cost about 120 to 130 bucks. But the rules on those motorized breakers, if they're going to qualify as the disconnect, they also have to be hand operable. So sometimes the little tab will stick through the motor and you can wiggle the tab back and forth by hand, but the motor will still also separately operate the breaker. Otherwise, they need to be separate. The disconnects need to operate both poles, both positive and negative poles. Um, they can have the means to disconnect the neutral, the grounded conductor. They need to indicate if they're open or closed. And then there's some minimum ratings of what's the smallest disconnect size requirements. And this one's interesting. On a single circuit, you got 15 amps. Single family home, there's a minimum 100 amp mandate. So you can design a house and only specify a 100 amp service panel if you want to. You know, assuming that the other parts of code that we talked about before are met, you know, square footage being one of them, or you do a calculated load test. And then we get to the all others of 60 amps. And what we'll see later on is that for supply side connections, they're really looking for a 60 amp connection on supply side. Yeah, as far as the minimum cable gauge and rating for that supply side connection. Not that you know, you can have a 60 amp rated main breaker and a 60 amp rated cable and then plug in a 20 amp microinverter. But most of those supply side connection taps on the market are for heavier gauge cable that is associated with 60 amp service. Up further than that. The special rules for 600 volts, including additional clearances for roadways, rail lines, water, you know, for additional disconnects. You know, we have 225.52. We have electrically operated disconnecting means, additional requirements, including a indicating switch on the directory plaque. You know, sometimes like the requirements from the knife switch disconnect at the residential level, that knife switch disconnect is not part of code, but often the inspectors are treating your residential arrays kind of like distributed power systems, and they're used to seeing knife switches on distribution stations and substations, and so they like to see them on your solar array as well. um let's see. So substations have a warning sign that says each operated isolating switch or disconnecting means shall bear a warning notice to the effect that contacts on either side of the device might be energized. A permanent, legible, single line diagram of the station switching arrangement, clearly identifying each point of connection to the high voltage section, shall be provided in a conspicuous location within sight of each point of connection. So on a substation, wherever you connect to high voltage, you have to provide a permanent placard of a single line diagram showing that switching arrangement. And when you get into, say, commercial design, and you might think, well, what are all the signage requirements that I'm going to have to get into? Here you see a call out that says, well, for substations, which are higher voltage systems, I need to have a plaque with a single line diagram identifying the points of interconnection. And, when you get into, it's not uncommon on commercial inverters that are going from the 600 volts of the array into the 480 voltage of the utility primary to put a single line diagram, around the inverters as well. So what I'm saying is if you're thumbing through code and you look at just a general section that says services and it says you have to put a single line diagram placard here if it's over 600 volts, such as at a higher voltage substation, you might find that when you get into the 1,000 volt section of the inverter equipment down in section 690 or past that, that they have similar requirements. Number of services. A building or structure shall be supplied by only one service except for these special conditions. I think I'm kind of repeating slides here. Conductors, one building or other structure not supplied through the interior of another. So if I have a row home, I'm not allowed to take the power lines from outside the building and then put them through the floor of another building and then tie those into a third building on the other side. Unless there's special conditions like I'm burying them in concrete or putting them in a concrete raceway, or there's a vault, that's just a concrete barrier around where the cables are going under. So essentially it's saying, hey, the cables need to be connected if they're going, or protected and heavily protected if they're going from unit to unit. Basically, they have to be encased in concrete. Okay, so then we have other conductors in the same raceway or cable are not allowed except for grounding conductors, bonding jumpers, and load management control conductors with overcurrent protection. And then we get another raceway seal call out that says, you have to seal your raceways. And we've already seen those scenarios when we were talking about feeders, and they're the same for services, which are a specific type of feeder and therefore coming after the feeder section. The requirements are pretty much the same, but feeders and services cannot share conductors with load devices. Same clearance requirements. Insulation. So service lateral conductors shall be insulated, except a grounded conductor shall be permitted to be uninsulated if it's bare copper in a raceway, or bare copper for direct burial, or bare copper where part of a identified cable. So without getting into that, there's sometimes you'll be using bare copper on a job site, but otherwise, like your neutral wire needs to be insulated. That would be a grounded conductor that has insulation on it. We have services, a call out being not smaller than number 8. Then we get a protection from damage where entering a building, they need to be protected in a raceway. Spliced conductors. So, when I there's the grounding system that needs to be permanently spliced. And so when you're running your copper wire, your bare copper wire up to the rooftop to land on the solar arrays and ground it, you may want to run another section of ground off to another subarray. And the only way to take two pieces of copper and put them together and consider them to be permanently connected is to take a crimping tool that is hard as heck to use because it's so large. You know, number 6 and number 8 copper are pretty thick, and you put a crimp around the two pieces of bare copper, and then you press this thing together as hard as you can and permanently crimp them together. It's not nearly as good as using a continuous run of copper, but it's considered to be continuous. You know, putting an acorn to connect your bare copper to your ground rod, will require protection. So, conductors need to be protected. Service conductors are permitted to be spliced and tapped, but only under certain conditions. So if you're inside an electrical box for a supply side tap, you are allowed to tap onto your service conductors. And how many service conductor sets can you have going into a building? As long as they are grouped together. If you have a special need to have more than one set of service entrance conductors, such as buildings with more than one occupancy, you can have 2 to 6 disconnecting means grouped together in one location from one service drop. All right, so for service conductors, their sizing based on 125% of continuous loads plus 100% of non-continuous loads. And then it says grounded conductors not connected to overcurrent devices shall be permitted to be sized at 100% of the total load. And so what that's saying right there is that the neutral wire, if it's not connected to an overcurrent device, is permitted to be sized at 100% of the load with no additional 25% allowance for the continuous load. And what that means is there are situations where the neutral line can be undersized, and it might save the client a little bit of money. However, in solar, you're generally not undersizing the neutral just to avoid any mistake for the time being. All right, so let's see where we're at here on time. To kind of finish out section 230 before the end of class, just give me a moment here. Where did my presentation go? We have the neutral conductor shall be, the size of it is governed by a particular table in National Electric Code. Where an AC system under 1,000 volts is grounded, the neutral is routed with the ungrounded conductors to each service disconnect. So your neutral is going to be running throughout the system. Now let's look at this wire diagram here. Now we have let me get my laser pointer out. We have our grounded module frame going onto a ground bar. So this might be inside a PVC box. So instead of the ground rod going on from the metal frame to the rack to the box frame, we're just making the ground inside this ground rod. And then that's carrying the equipment ground to the metal inverter box. And then this is also going, maybe that's a permanent crimp, but it's also being connected to the ground bus on your main service panel. So we see a fully interconnected grounding system, and there's special rules on what constitutes as a grounded system. So often with solar arrays, you actually need two grounding electrodes rather than one grounding electrode, particularly when you're using ground rods. And so we see two grounding electrodes